So welcome students. We're going to officially start off learning about hypothesis testing with the t-test, specifically the independent and dependent samples t-test. In the textbook, this covers chapters 11 and 12. So I have this week's lecture videos separated in 3 different parts. And so our objectives for this chapter are to understand, calculate, and apply the 5 steps of hypothesis testing to independent samples t-test. And this is part 1 video. Objective number 2 is to understand and apply the 5 steps of hypothesis testing to dependent samples t-test, also known as paired samples t-test. And this is video number 2. And the last video is understanding how to interpret SPSS output for both types of t-tests. We'll also see some key terms, specifically effect size and homogeneity of variances, which you'll find here in part 1. So let's start off with chapter 11, learning about independent samples t-test. So here's the scenario. Dr. Fry, a Cal State Fullerton researcher, is interested to see how blood doping can impact a cyclist's overall time on a 30-mile course. He selects 2 groups consisting of 10 cyclists each. One group he provides with EPO, a hormone used in blood doping. This is essentially the treatment or intervention group. And the other group receives no treatment at all, and this is also known as the control group. After treatment, he records each participant's overall time in minutes. So his question is, how could Dr. Armstrong identify if EPO had an effect on cyclists' overall time? Well, he could test whether or not there was a significant difference between the 2 groups in overall time. See what we did there? So this is how we're going to think about independent samples t-test. We're trying to see, is there a difference between 2 different groups? So the independent samples t-test can also be called the independent means test, and essentially we're looking to see if these 2 groups, these 2 independent groups, differ on their means. So essentially we're comparing these 2 groups on one variable, and that one variable is our dependent variable. So we have our 2 groups. The first group is our doping group, and then we have our non-doping group, and we're trying to see and compare if these 2 groups differ on our dependent variable, which is the average time taken to complete a 30-mile course. Let's go ahead and walk through our steps of hypothesis testing, steps 1 and steps 2. So step 1 is stating the null hypothesis along with the equation. So what are we stating here? We're simply stating that there are no differences between the doping group and the non-doping group on average time to complete a 30-mile course. And how would we write out the null hypothesis equation? Well, H naught is equal to mu of D, which is the doping group, equals the population mean of those non-doping. Step 2, the alternative hypothesis and equation. Well, we can do 2 different ways. So let's start off with a non-directional research hypothesis and equation. So H1, there is a difference between the doping group and the non-doping group on average time to complete a 30-mile course. We can write out the equation such that H1 is X bar of the doping group does not equal the X bar of the non-doping group. And if you wanted to do a two-tailed test, well, if we did a two-tailed test, which group do you think is going to be better or faster or slower in terms of their average time to complete a 30-mile course? We have our doping group and our non-doping group. Do you think our doping group is going to be faster or slower? Most likely faster, right? So we can hypothesize, writing a directional research hypothesis, that the doping group has a faster average time to complete a 30-mile course than the non-doping group. So we can write out a directional research hypothesis equation. X bar of the doping group is less than X bar of the non-doping group, right? We're saying that the average time of the doping group is going to be faster, so they're going to have a smaller number, right? A faster time, a smaller time in terms of minutes than the non-doping group. So we completed steps 1 and steps 2 of independent samples t-test. Okay, so step 3. Ready for your freaky formula? Here we go. Look at that. What in the world is this craziness? So let's just break it down. Really, what's going on here is it's just simply a ratio. That the numerator is simply the difference between our two sample means. We have group 1 mean and group 2 mean. Now what's the difference? And the denominator, all this craziness, is simply the variability of the groups. How much variance, how much dispersion is there among our two groups within the groups themselves? So here we go. But the nice thing is we'll be working with a much more simplified version. So here's what we'll have. X bar of 1 minus X bar of 2 over the pooled standard deviation. And even better, I will provide you with the pooled standard deviation every single time. So all you have to do is simply plug and chug. So here is the formula whenever we do a hand calculation for t-tests. Rule of thumb, deciding who is group 1 and who is group 2. If you're doing a non-directional research hypothesis test, it doesn't matter which one is group 1 or group 2. However, if you are positing a direction and you're positing a directional research hypothesis, put the group that is hypothesized to be bigger or smaller, whichever one it is, first. And this is usually going to be the intervention or the treatment group. You can treat them as group 1. And then the comparison group, which is usually going to be the control group, if you have a control group, can be group 2. Alright, so let's go ahead and calculate our t-statistic. Here are some descriptive statistics for both of our groups. A blood doping group completed a 30-mile course in an average of 98 minutes, standard deviation of 5.75, and the control group finished on average the 30-mile course in 120 minutes, standard deviation of 3.75. Here is the pooled standard deviation, 8 minutes. So let's calculate the test statistic. Here's the formula. Go ahead and pause the video and see if you can calculate t. Alright, so let's see if you were able to plug and chug. So, t is equal to 98 minus 120 over 8. Again, because we posited a non-directional research hypothesis, it doesn't really matter which one we put. But we also kind of had our directional one where we posited that our blood doping group was going to be faster. So in essence, we could have put them first. So if we did that, we would have a t equal to negative 2.75. Again, rounding 2 decimal places to the right. So now that we have our test statistic, we can move on to step 4, which is making a decision. And with making a decision, there are going to be certain tools that we're going to need, specifically 4 tools in order for us to actually make our decision. The first tool is our actual test statistic, in this case, our t-tests, and we've done that already in step 3. So our first tool we have, t is equal to negative 2.75, we've got that. Our second tool, we need to determine our significance level and the tails that we're testing. So just like any inferential test, you have to identify what your alpha level is before you conduct your tests. So what's a commonly used one that we see? Alpha is equal to 0.05. This is giving ourselves 5% chance of being wrong, that we're going to reject the null hypothesis when in fact it's true. And what about our tails? Well, since we did kind of list both of them, let's go with first a non-directional. So non-directional research hypothesis is going to be which tail? 1 tail or 2 tails? 2 tails. All right. So why do you think this guy got this tattoo here on his back? It's kind of silly to have a alpha symbol on his back there. Well, maybe he felt he needed to be significant. All right, that was kind of silly. Okay, so now we have our second tool that we need, which is essentially our significance level and our tails. And we know that we have our alpha level set at 0.05, and we're conducting a two-tailed test. Our third tool, degrees of freedom. Well, degrees of freedom, really what it is a nice estimation of our sample size. So we'll see that the formula for degrees of freedom for independent samples t-tests will need our sample sizes. So, as we'll see in the coming weeks, Bobby the Bear will always tell us what our degrees of freedoms are. So Bobby the Bear, what's our degrees of freedom for independent samples t-test? Well, degrees of freedom is equal to sample size of 1 minus 1 plus the sample size of 2 minus 1, or sample size of 1 plus sample size of 2 minus 2. Thanks, Bobby the Bear. So here we go. We can either decide to use one of these two formulas for our independent samples t-test degrees of freedom. So thinking about our sample, we have 10 cyclists in each group, gives us a total sample size of 20. So we can simply plug and chug, and we get a degrees of freedom of 18. And the thing with degrees of freedom, again, because it's all related to sample size, and it's a good estimation of our sample size, they matter because the larger the sample size that we have, the smaller the critical value. And we'll see what the critical value means and what it is and how it's important. But if you think about inferential statistics and sampling error, the more people we have in our sample, the better we can generalize our results from our sample to the population. And the more likely that our sample is going to look like our population. So our third tool, degrees of freedom, we now have degrees of freedom of 18. So our last tool that we need in order for us to make a decision is finding out our critical value. And we have a critical t-score table that you can find in the back of your book, and I'll always provide you with the table as well. So let's take a look at this. Time to introduce another table. No, not that type of table, this table. So this is our critical t-scores, or also known as our critical values for our t-test. And we're going to use this information to help us decide whether or not there's a significant difference between our groups. We're going to use these critical values and compare these critical values to our calculated t-test that we had in step 3 to actually make our decision. So let's take a look at what we have here in this table. We have our alpha level. We see we have alpha level set at 0.10, 0.05, 0.01. So depending on you as a researcher, again, we get to decide and set our significance level. We also see we can decide on either a one-tailed test or a two-tailed test. And then we have our degrees of freedom. And with these three pieces of information, tails we're testing, alpha level, and degrees of freedom, we can then find our actual critical value, our critical t-score. So let's go ahead and find our critical value for our t-test that we're conducting. So we have a two-tailed test, so we're going to go and look on the right side of this page. We know that our alpha level is set at 0.05, so we're going to look down this column. And then we have our degrees of freedom that we calculated to equal 18. So we're going to look on this row to then triangulate and give us our critical value of 2.101. And the reason that we have a plus and minus in front of this critical value is because we're conducting a two-tailed test. And we know that each tail is going to be a mirror image of each other, and down that middle, which is essentially going to be the zero or the mean, is the reference point. And this is on each side going to be negative 2.101 if we're looking at the left tail, or positive 2.101 for the right tail. So this is how we use our table to find our critical value, our last piece of our tool for step 4. Here we go. We now have all the tools we need to make our decision. So let's go ahead and make our decision. So here we have our normal distribution. And because we're working with a two-tail test, let's focus on this curve here on the left. And in order for us to accept the alternative, where we're rejecting the null hypothesis, our t-test, if we're looking at the left tail, or a negative critical value, our negative t-test statistic needs to be smaller than our negative critical value. Or if we have a one-tail test, looking at the right tail, or just doing a two-tail test and looking at the right side, our t-statistic has to be greater than our critical value in order for it to fall in the rejection region so we can accept the alternative. So given that rule, if this is our statistics, our t equals negative 2.75, and our critical value is 2.101, well, we know that here would be our test statistic, here would be our critical value. Well, we see that our test statistic actually falls within our rejection region. Not only that, we know that our t-statistic is less than our negative critical value, therefore we're going to reject the null hypothesis and say that yes, there are significant differences. So now we made a decision and we know that we're going to reject the null. That's awesome. We know that there are significant differences between our two groups, but we don't really know how much they differ. We just know that they do differ significantly. So this is the idea of effect size. Effect size provides a measure of how different two groups are from one another. So Jacob Cohen, the guy that we see here, is a very famous statistician who really helped us establish and understand effect sizes. And one of his measures is called Cohen's d. And our formula for Cohen's d, the sample mean of group 1 minus the sample mean of group 2 over the standard deviation. And notice that we're taking the absolute value of this calculation to figure out our effect size. So again, this is very similar to our simplified t-test. If you remember, our test statistic for t is simply the same thing that we see here, except that we're dividing by our pooled standard deviation. In this case, when we're calculating our effect size, we're going to use either the control group standard deviation if you have a control group, or if you're doing a dependent samples t-test, which we'll see, you then will use the pre-test, the before test score. And so once we calculate our d and take the absolute value of that, we have ranges where if your d is less than or equal to 0.20, it's considered a small effect size. If it's less than or equal to 0.50, it's considered a medium effect size. Greater than 0.50 is considered a large effect size. And so if we take our example, we have our mean to standard deviations for both of our groups. Go ahead and plug and chug. So we have 98 minus 120 over 3.75. Again, we want to use the control group because we have a control group here. Don't use the treatment group standard deviation, but use the control group standard deviation. We end up getting a negative 5.86. Make sure you take the absolute value because you don't want to say that, oh, well, this is actually a very small effect size because it's negative 5.86. Well, no, we took the absolute value. What we're actually looking at 5.86, which indicates a very large effect size. In fact, a huge effect that EPO had on this cyclist's time. So our last step, stating our conclusions for independent samples t-tests. We always want to report the mean and standard deviation for each group, your calculated test statistic, your degrees of freedom, your p-value, which we get from SPSS, or your significance level, which we set at usually alpha 0.05. But if you find significant differences, then you also want to report the mean difference, the effect size, and your D. So here's a template that you would write out for your interpretation, for your conclusion. There was a significant or not a significant difference between group 1, stating their statistics, and group 2, stating their statistics, on whatever your dependent variable is. We have our T statistic, followed immediately by degrees of freedom in parentheses, and then stating our T statistic, minus, if we know our p-value from SPSS, we put p equals. But if we don't know, and it's a hand calculation, we'll do p is less than or equal to 0.05, which is our alpha level. If it's significant, then you follow up with this last sentence, that the mean difference of, whatever that mean difference is between group 1 and group 2, indicated a small, medium, or large effect, and then we state our D. So here's how we would state our final conclusions for our cycling example. There was a significant difference between the doping group and the non-doping group on the time to complete the 30-mile course. Notice that we're stating the mean and standard deviations for both of our groups, followed by our T statistic, negative 2.75, degrees of freedom in parentheses, p is less than or equal to 0.05 because we don't know the exact probability of the null hypothesis being true. We just set it using our alpha level. Because it's significant, the mean difference of 22 minutes indicated a large effect. D is equal to 5.86. So the last thing we'll talk about in part 1 and about independent samples t-tests are the assumptions related to this type of test. In order for us to really look at our results and have some meaning from it and feel confident about it, there are some assumptions we have to take into consideration whenever we're analyzing our data and collecting our data. One of those is that we independently and randomly sample from the two populations. So those who are the doping group and those who were the non-doping group, we randomly selected those 20 cyclists. And each of those participants had no influence on us selecting any other ones. So they were randomly selected and they were independently selected. That's one assumption. The other assumption is that we assume normal distribution on our dependent variable, that it's unimodal and there's little to no skewness. Right? We want to see a normal distribution, which allows us to really utilize our normal distribution curve to test our probabilities and test our hypotheses. And the last assumption for independent samples t-tests is the idea of homogeneity of variances. And essentially this is saying that the variances, the standard deviations, between the two groups are roughly the same. So take, for example, this image. We have males and females, and we have the same central tendency measure. They both have the same mean of 6. Looking at their dispersion measure, their variability, we see that it's roughly the same, 5.87 for males, 5.62 for females. It's very, very slight variability, but essentially the same variance. However, in this example, we see that we have the exact same mean for both males and females, but take a look at the distribution. Look at the kurtosis. Look at the variability for males and females. There's more variability among the males compared to the females. Less kurtosis in males, more kurtosis in females. And so because there is no homogeneity of variances, we would call this heterogeneity of variances, that they look different. As opposed to this first image here, where we have equal variances, they are similar. Homogeneity is simply similar, the same variances. So one of the assumptions of independent samples t-test is that we want our groups to have the same equal variances. We want to assume equal variances. And we'll see how this translates to looking at SPSS output and Levene's test. Alright, so that wraps it up for part 1 video lecture for chapter 11. We've gone through essentially looking at the 5 steps of hypothesis testing, how we calculate our t-test by hand, And then go to part 3 to learn about how we look at SPSS output a little bit more related to independent samples t-test.